So to talk about simulating active feedback control, let's first talk about what we mean by um, what are feedback loops in general. So I'm going to talk a little bit about what is a feedback loop, what do we mean by feedback loops, and how does GoldSim actually simulate these feedback loops. We'll then talk a little bit about what I mean when I say active feedback control. All right, and finally, we'll talk about how do we go about simulating active feedback control. What is the right way to do it, and what is the wrong way to do it? And when I say the wrong way is these are the issues that we get all the time. Why does my model behave incorrectly? Look what it's doing. What am I doing wrong? So I'll show you some examples of the wrong way to do feedback control and how it can get you into trouble. But let's first talk a little bit about feedback loops in general. You know, there's an entire science behind this. For those of you who have read about system dynamics, they put a huge emphasis on understanding feedback loops. In fact, it's all about feedback loops. Systems behave according to different feedback loops, and it's a very nice way to look at things. It's a little bit difficult to apply it to engineering problems because the whole world isn't feedback loops. It's important in many systems, but it's not the whole story. GoldSim can handle stuff that system dynamics does, but does a lot more because the whole world isn't feedback loops. But let's talk about feedback loops a little bit. There's two types of feedback loops. There's the self-reinforcing feedback loops. These are positive feedback loops, and there's negative feedback loops. And these are self-correcting. And a negative feedback loop leads to equilibrium. And you'll see when we're going to talk about active feedback control, active feedback control involves using negative feedback loops to make a system behave the way you want it to behave. But let's talk a little bit about what we mean here by positive and negative. Let's just look at a very simple example of a system that has feedback loops. Here's a feedback loop, chickens and eggs, and this is a positive feedback loop. So, and this is the nomenclature. This is called a causal loop diagram. So the more chickens we have, the plus sign means the higher our egg production rate. The higher our egg production rate, the more eggs we have. The more eggs we have, the more chickens we have. So this is a positive feedback loop. And if this were the only loop operating in the system, we would grow. In fact, the system would grow exponentially until the surface of the earth was covered with chickens and eggs. But of course, there's other feedback loops and negative feedback loops that control this. And there's a lot of negative feedback loops that would control a system like that, things like food. I'm just going to show you one. Here's a negative feedback loop that controls the chicken population, and it's their road crossing rate. Okay, so here I have chickens. The more chickens I have, the higher the rate at which I have road crossing. The more road crossings I have, the higher my chicken kill rate is. The higher my chicken kill rate is, the lower the number of chickens I have. Because I have an odd number of negative signs in this loop, it's a negative feedback loop. So this model has these two loops, and this, by the way, this type of loop tends to go to equilibrium. So this model has these two loops, and they're competing against each other, and one can dominate. Let's just look at this model. Here's the actual model that I've just drawn there, and there's our positive feedback loop, and there's our negative feedback loop. All right. These are our input parameters. What's our initial number of chickens, our egg production rate, the incubation period, the rate at which chickens cross the road, and the rate at which chickens are killed if they go across the road. So I've just created a little dashboard here so we can simulate this system with the key input parameters: initial number of chickens, the fraction of chickens who are laying eggs, the fraction that attempt road crossings, and the fraction of road crossings that end badly. So here we've got 25% of the chickens in any given day are going to attempt to cross the road. 30% of those road crossings end badly. So let's just try that guy, and you'll see if we run this model, the positive feedback loop is dominating. right? So we're not really killing enough chickens on the road, and we're still rising quite a bit. Now, what we can do here, of course, is increase, let's say it's a highway. So now we're going to basically say, well, 65% of the chickens don't make it across the road. All right, so let's try to run that model again and see if it changes our results. And it does. We start to oscillate, but we're still going up, right? So now we have a competition between these two feedback loops. Let's continue to play with this feedback loop, and maybe we'll say more chickens are crossing the road. Now we're killing more chickens than we're producing, and so basically eventually we're not going to have any chickens at all. So you can see the trade-off here. Somewhere in the middle, you'd hit a stable situation probably. If you played around with this enough, you'd actually see a situation where these two guys start to balance each other. And you might you'd get a stable, maybe an oscillating stable system. So eventually that's what you would get to, because we have these two competing feedback loops. All right, so that's a real kind of simple, silly example. Let's now talk about an engineering example. And this is a very simple water example that happens. Anybody who's doing a water management model has to simulate this feedback loop. So we have a pond that has water flowing into it, and we have no control over the inflow rate. And nothing leaves the pond except water that's evaporating, and the evaporation rate is a function of the surface area. All right, well, it turns out this is basically controlled by a very simple negative feedback loop. Right? What is that negative feedback loop? It's this one guy right here. So the pond volume, as the pond volume increases, the pond area increases, unless you have vertical walls. As the pond area increases, the evaporation rate increases. As the evaporation rate increases, the pond volume decreases. So that's a negative feedback loop. So let's go ahead and look at that model. And that's a very simple little evaporating pond model. So there's my pond. Here's some inflow into my pond, say 10 cubic meters per day. I have a evaporation rate of 0.7 centimeters per day, and the actual evaporation rate and volume per day is that rate times the surface area. My surface area is actually a function of the pond volume. I just created a lookup table here to convert a pond volume to a lookup table to an area. So that's all we've done there. And there's our feedback loop. There's our negative feedback loop. As the pond goes up, the surface area goes up. As the surface area goes up, the evaporation goes up. As the evaporation goes up, the pond goes down. And so if you were to run this model, you actually reach a steady state. In this very simple model, we have a constant inflow. You actually reach a steady state. And it stays constant unless I were to change my inflow rate or change an evaporation rate, just a constant system at equilibrium, at dynamic equilibrium. So very simple negative feedback loop. It's not an active feedback loop because we're not controlling it. That's just the way the world works. Let's talk a little bit about how GoldSim does this. You may be curious, how do I do this? Because those of you who are spreadsheet modelers, if you were to build that, you would get some kind of recursive error. How does GoldSim actually model this system? Well, it turns out the way GoldSim models a system like this, you have to understand, and you can look in the documentation about this, certain outputs in GoldSim are state variables. All right, an example of a state variable is the volume of water in a reservoir, or the quantity of something in a reservoir. It's a state variable. State variables always have an explicitly defined initial value. That's a very important point. They have an explicitly defined initial value. It turns out, and you can read about the theory in the manual more, but it turns out that as long as you have a state variable in a loop, GoldSim will can calculate that system. there's no state variables, you will not be able to create the loop. GoldSim will say this is recursive logic. But if you have a state variable, it's going to be able to do it. Essentially what it does is as follows. We know what the value is of this guy initially. Therefore, I can calculate the surface area. Therefore, I can calculate this. Then I can update this guy. So it goes and looks at his initial value, calculates that one, then updates him for the time step. That's basically, in simple terms, how we would handle a looping system like that. Okay, just wanted to kind of put that out. Now let's talk about active feedback control. And this is where we see people run into a lot of problems. So remember, a negative feedback loop is self-correcting and leads systems toward equilibrium. So active feedback control involves the intentional design of a negative feedback loop in your system. And this is everything in the world. The world is full of active feedback loops. In economic systems, tax incentives, policy decisions, a thermostat. All right, these are all intentional negative feedback loops in a system. Let's talk a little bit about how we would simulate a negative feedback loop. In terms of kind of the generic way of thinking about GoldSim, the most common types that you encounter is you're trying to manage a reservoir to a target. All right, it's a classic example, and the example of that is a thermostat. In that case, your reservoir is really the amount of heat, the proxy being temperature, in the reservoir, and you're trying to manage to a target. All right, and so we're going to use a negative feedback loop to manage a reservoir to a target. All right, in the water management world, you're trying to maintain a water level in your reservoir. Sometimes your system is not really managing it to a target, but it's doing some management at the bounds. As the thing approaches, being empty, or as it approaches some upper bound, do something. All right, so there's another way that we might need to use an active feedback loop to control. But in both cases, what we're doing is we're trying to control the quantity of something in a reservoir. For a thermostat, it's heat. For a water system, it's the water level. So let's look at a simple example and see how we would want to model this. So let's say we have a pond and it starts empty. There's no water in the pond. Okay, but we have water entering the pond, and it's entering at about 100 cubic meters per day. We have some stream flowing into a pond, but we're going to model this as in a stochastic manner, so it's not constant, it's bouncing around a little bit. And what our goal is to keep that volume around 300 cubic meters. So our target is we want to keep the water volume at 300 cubic meters. Now, obviously in the real world, we're not trying to control the volume, we're trying to control a water level, but I've simplified the example here because you can always convert a volume to a water level using a lookup table. So we're just going to stay with volumes right now. So we're going to try to keep the volume at 300 cubic meters, and the only way we can do that is by using a pump that operates at a particular rate. All right, so that's what we have that we can use. How are we going to do this? Here's the first thing people do, all right, when faced with this problem. They say, well, that's simple. I'm just going to have some logic for what the pumping rate is. And I'm going to say if the pond is above my target, if I'm above 300 cubic meters, pump. If I'm below 300 cubic meters, turn off the pump. And this is the first reaction that people try. All right. Well, let's just do that. Let's see what that model would look like. And here's that model. So here's my inflow. I'll just show you what we're doing here. I've got an inflow that's just a stochastic, so it's just bouncing around, right around 100 cubic meters. I had an initial volume of 0. I have a target of 300 cubic meters. All right, and then my pumping rate is just this guy here. It says that the pond is greater than the target, pump it at that rate, which in this case was 200, else turn off the pump. And that guy is just the withdrawal rate from the reservoir. All right, very, very simple model. Well, what happens when we run this model? this is the result we get. All right, so we will get an email once a week that says my system is oscillating. What's wrong with GoldSim? So there's nothing wrong with GoldSim. There's something wrong with your model. All right, this system, if you think about it, is going to cause the pump to turn on and off every time step. All right, boom, 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 boom. The time step is totally arbitrary. If I made my time step a minute, the pump would turn on and off every minute. If I made it a second, the pump would turn on and off every second. All right, there's no way the real system operates this way. It just won't work, all right? The pump wouldn't last very long. You would never design a system that had this logic built into it, all right? So this is something we see a lot, but it's going to result in oscillatory behavior. It gets even worse, by the way, if your target is actually a bound, okay? If your target is actually a bound, and I can't remember if I have an example for this one. Yeah, okay. Here's a system. It's the same system I just built, but my target now is 0, and that's the lower bound of the reservoir. It's worse. Why is it worse? That's what your result looks like. Why is it worse? Well, the problem in this case is that if you recall, GoldSim, when it hits a bound, a lower bound or an upper bound, inserts a time step. All right? So essentially what's going to happen now if your target is at the bound, GoldSim is inserting time steps every microsecond. It says, oh, I'm above the bound, now I'm below the bound, now I'm above the bound, now I'm below the bound. And it's oscillating like crazy. In fact, what happened, this is the most common thing we see. People say my simulation just ground to a halt. It takes 3 hours to run. What's happening? And we know exactly what's happening. It's oscillating at one of the bounds because you've got a situation where you're turning on and off something right at a bound. All right. And you may say, oh, I would never do that. No, we see this all the time. We see it all the time. All right. It's a very common mistake that people make. Okay. So we need to avoid this type of logic in our models. And it's not, this has nothing to do with GoldSim. This is not how anybody would design a real world system. No pump would turn on and off with this logic. It just doesn't work that way. Obviously, in a real world, you're not monitoring the volume, or you're monitoring the water level probably, but it's never going to work like this. So how does it really work? All right, well, let's try something else. Now let's say we have a variable speed pump, okay? And now we're going to say the pumping rate is a function of how far we are from the target. Well, that sounds a little bit more reasonable, okay? So now let's take a look at that guy, okay? And here's a variable speed pump. So now what I've said is, now what I'm going to do is I'm going to take a look at the pond volume, or the water level in the real world. Okay, I have a target, but I'm going to monitor the difference between what's in the pond and what my target is. And my rate, my pumping rate, is going to be a function of that difference. Basically, as the difference goes to 0, the pumping rate goes to 0. Okay, then my withdrawal rate is going to look like this. It's basically going to be some basic rate plus this variable rate. The variable rate is going to go to 0. The pumping rate doesn't go to 0 because I still have inflow. All right, I have some base rate and my variable rate goes to 0. All right, as I approach the target. And if I run this model, you know, here I started above. Here you see the pumping rate in the pond. Oh, that looks great. That looks perfect. I really like how that system works. That looks realistic to me. It's approaching my target perfectly, and look, my pumping rate approached 100, and it's just kind of bouncing around 100 based on the noise. So that looks good, and that may be realistic. We'll come back to this in a minute. That may be realistic, okay? Seems to work very well. But a couple things we have to keep in mind here. This requires rapid and continuous control over the pumping rate, all right, because we're adjusting it every time step. Is this realistic? Maybe, maybe not, okay. Another thing it requires, however, is the forecast of the inflow. And you say, what do you mean it requires the forecast of the inflow? Well, my pumping rate is a base rate plus a variable rate. My variable rate is just reacting to the difference between my target and here, but there's a base rate on top of this, all right? My base rate is just my approximation of what I think my inflow is going to be, all right? So this method of control requires you to have some forecast, some guess of what the inflow is going to be. There's nothing wrong with that, but you just need to understand that that method requires you to have a forecast of the inflow. Okay, now another variation of what I just showed you is not to have a variable speed pump, but have multiple pumps, okay? And so we can do the same thing. I mean, a multiple pump model is just a discretized variable speed model. You kind of turn the second pump on at a certain at a certain pumping rate and so on, and it works fine too. And here you see we had one pump on, then we had two pumps. We had two pumps on, then we had one pump on, and this system works fine too. Okay, so it's just a discretized version of a variable speed pump. So this model also works. I'm modeling two different pumps turning on based on where we are relative to our target. So basically, I'm saying if we're below the target, don't pump at all. If we're at a second level, have a base pumping rate, otherwise double the pumping rate. So that system works well too. And so what we can conclude from this, you say, oh, we're done, no problem. Well, they do work well. If variable speed is realistic, you can use that. If multiple pumps are realistic, you can use that. But keep in mind, both examples are based on a critical assumption that the inflow rate can be forecast. Okay, the inflow rate can be forecast because the pumping rate always has a base pumping rate, which basically represents our best forecast of what the inflow is going to be. All right, so that's a critical assumption. All right, which means that your control system it's monitoring two things: the current volume or water level and the inflow rate. It knows those two things. All right, so just keep that in mind. That is not how a thermostat works at all. All right, that should give you a clue that a lot of feedback systems do not work that way. The thermostat monitors the temperature. That's what the thermostat monitors. It's a state variable. It does not monitor the rate at which heat is leaving or entering the house. How would you do that? Very difficult to do. It does not monitor that. That's equivalent to monitoring the inflow rate. The thermostat does not work that way, okay? So for a water management system, what we would really like to have is to have a solution that all it does is monitor the water volume or the water level. That's all it monitors, and it makes decisions based on that. Doesn't need to know the inflow rate. It turns out you can't, all right? But you do not have to monitor the inflows and the outflows. You can't just monitor the water volume, but you do not have to monitor inflows and outflows. So in order to understand that, how does a thermostat work? How does it really work? It uses a deadband. That's how a thermostat works. All right. What do we mean by a deadband? Well, deadband works like this. You might set your thermometer, say 70 degrees or whatever, but there's actually two things involved in a thermometer. There's not just the temperature you set. So basically, it's going to say, I want to turn on at a certain temperature, maybe the temperature that you set, and then I'm going to turn off when I reach something else. So there's this band in between where sometimes the heat is on and sometimes the heat is off. So I'm at 69 degrees here. I'm pumping. I'm putting the furnace is on. Here I'm still at 69 degrees. Now it's off. All right, so that's essentially how a simple thermometer works. All right, but what's really happening is the thermostat is monitoring two things. It's not monitoring the inflows, it's monitoring what's the temperature, and it's also saying, oh, am I on right now? Something simple to do. Am I on? Okay, is the heat on right now? So for a pond example, we're going to do something similar. We're going to turn the pump on when the volume reaches a certain level, and we're going to turn it off when it reaches a different level. Instead of turning on and off at 300, we're going to turn on at 305, we're going to turn off at 295. Okay? In order to do this, we actually need to track two things in the GoldSim model. We need to track the volume, or the water level, and the pump state. Is the pump on? Is the pump off? Okay? So how do we do that? We're going to use a status element to do that. So here's our model. Okay. So in this model, again, I've got my inflow. Let's just go ahead and run this guy. Here's my inflow. It's just bouncing around. I have an initial volume of 100. Okay. I have my pumping rate at 200. I have my target. I'm going to say my target is 300, but I have a band around that target. Here I've put a band of 20, which is actually, so that's not what I've described here. So I have a band of 20. What does that mean? So I have the status element, and for those of you who are not familiar with status elements, let me just take a minute. Your model should be full of status elements. Status elements are really, really powerful elements. A status element has one output, true or false. Okay. You specify an initial condition, am I true or am I false? And then you specify triggers to turn it true or to turn it false, to turn it on or to turn it off. So in this particular case, my trigger, and the status represents the pump is on. It says, I want you to turn the pump on if the pond is greater than my target divided by half my band. So my band was 20. So basically, I'm turning the pump on when I get to 310, not 305. All right, I'm going to turn my pump on when I get to 310. All right, and I'm going to turn the pump off when I get to 290. All right, so that's all we're doing. We're keeping track of should the pump be on, should the pump be off. My withdrawal rate then just says, hey, if the pump is on, pump at that rate, else pump at 0. So if you run this model, you see this. All right, it still oscillates. Of course it has to oscillate. The pump is coming on and off, but it's not oscillating every time step. You are controlling the rate at which this is happening, and it's set just like your furnace doesn't come on and off every minute. There's this band, and it comes off, then the house cools, then it comes back on, then it comes back off, then it comes back on. That's what we're doing here. So here's our pump on. There, our pump turns off. Thing starts to fill up again because we have inflow. Turn the pump on, and so here is how our real system is working. Yes, we get some oscillations right around our target. Okay, and obviously, if you did not want your system to ever exceed 300, you would set your band below 300, right? You wouldn't set it above 300. You wouldn't set it at 300, right? Because this is going to go above 300. In fact, we didn't turn the pump on until we hit 310. Right? We're trying to manage it right around 300. Okay. So that's a very, very simple system. I want to point out one other thing that's important here that you may not be aware of, and that is how are we triggering this status element? How are we triggering the status element? So let's go look at our trigger for our status element. So I'm going to say turn this guy to true when this statement becomes true. All right. turn this guy to true, turn it to false when this statement becomes true. There's actually two different ways to do this in GoldSim, okay? There's the way you see here, which is not completely accurate, and then there's a more accurate way, and I want you to understand them, okay? In order to understand this, you have to ask a question, when does GoldSim evaluate that? It evaluates that every time step. So if you've got a 10-day time step, it's going to go and check if that's the case every 10 days, okay? Well, if you've got really high flow rates, you might be way above this by the time GoldSim goes to check it, all right? This only checks when there's a time step, a specified, what we call a scheduled time step, all right? There's another way we can do this that's much more accurate. I can say at stock test. And at stock test slows the model rundown. But here's what GoldSim's going to do. It's going to monitor that thing called pond. And it's going to insert a time step exactly when this statement becomes true. So if you've got a 10-day time step, all right, if this statement becomes true at 11.45 days, GoldSim is going to insert a time step and turn the pump on. All right, it's going to slow your simulation down, but you will never go above, in this case, 310. In this case, you will go above 310, right? Because you might not check this until after we're above 310, right? Big difference here. So this is only evaluated, and on true is only evaluated at every scheduled time step. This particular model, let's see, he had scheduled time steps. It was a 1 hour time step. So every hour it's going to go look at this particular case. All right, so this could, if in between we hit 310, too bad. We're not going to look until the next hour. This is going to catch it exactly when it hits the boundary. So keep that in mind. This will insert a time step for you. It's going to monitor. This type of condition, by the way, only works when you're comparing it to a reservoir. So if you just said X greater than Y and X and Y were expressions, you can't do this. GoldSim will give you an error message. If you have what we call an at stock test trigger, the thing you're testing is a reservoir. And the reason is GoldSim can monitor a reservoir very easily. It can't monitor just an expression. It can't predict what's going to happen to an expression, but it knows what's happening with a reservoir. So this is the most accurate way to model this particular situation. Okay, there's another issue we have with active feedback control. We've just shown a system where I was monitoring it, at some arbitrary level. Now I want to control it at a bound. All right, and the most classic thing we see people do is they're worrying about a lower bound. We're approaching a lower bound. The reservoir is running out of water. All right, what do we do? Okay, well, as you saw, if this is done poorly, it can result in really, really oscillating behavior. That's what I showed you here. This was, we're basically turning the pump off. This says, oh, turn the pump off when it hits 0. Okay, you want to do that, that's what you're going to get. All right, that's not going to work. All right, you're just going to get nonsense. There's two ways that you can handle this. The first way is to use a deadband that I just described. Basically, I said, let's not turn off the pump at 0. Let's turn off the pump over a band. Turn on and off the pump. Put your deadband just above the bound. All right, that's one way to handle this. Another way to handle this is to slowly ramp the pumping rate so it goes to 0 in a smooth manner. Okay, it slowly goes to 0 in a smooth manner. Let me show you an example of what I mean by that. So here's a model in which we start at 100 and we don't have any inflow in this particular case. All right, the pump, and I'm going to pump water out of this guy, all right? But my pumping rate, okay, is going to be a function of how much water's in the pond, all right? And here I just put in a very, very simple linear a linear rate. When we're at 25, when we have a volume of 25 or above, we're going to pump at this pumping rate of 200. And then we're just going to linearly scale it down. So by the time we get to zero, the pumping rate goes to zero. So let me show you what we have here. All right. Essentially, here I'm above 25, so I'm pumping at 200, and we're dropping, dropping, dropping. As soon as I get to 25, I start to scale my pumping rate down so that it smoothly goes to zero. Now, can you do this? Maybe. It depends on what kind of system you have. Is it physically possible to do this? But if you do model the system this way, you slowly approach zero, so the pumping rate goes to zero as the volume approaches zero, so you hit zero and you just stay there unless some more flow comes in. All right, so this is a nice way to model the system. This is how your traditional system dynamics people would say this is how you should model a system like this, that the pumping rate should react to the volume and should scale down so that it smoothly approaches zero. Okay, so just to summarize what we covered here, very simple stuff. What we've talked about is not complicated, all right? And the two things I want you to kind of take home here is, you know, if you want to simulate active feedback control to control a level in a reservoir, use a deadband around your target level, all right? If your target is at your lower bound or upper bound, use the deadband just prior to it, right? So you don't get to it, because otherwise we're going to start to get oscillations. You can also, all right, slowly ramp inflows and outflows so they smoothly go to zero near your targets, as I just showed you right there. So there's another approach to dealing with active feedback control. But the thing you have to keep in mind, turning things on and off at one level, water above 300, turn it on, water below 300, turn it off, is going to result in oscillations. But more importantly, it's totally unrealistic. It's very unlikely that that's how your real system behaves, that your real system is designed to work that way. And that's really the take-home message. So when you're building a model that includes active feedback control, you have to represent what is physically realistic for your system. That is, what's it really doing? What is the real system doing? Okay? So for example, if you don't have a variable speed pump, you should not assume that your model is ramping smoothly. All right, it's ramping smoothly down. Because it either turns on and off. So you need to try to represent the system that you really have, and people often overlook this point. You know, look at the system that you have. How are the pumps turned on and off? What can you realistically do? How does it really work? And these are usually complex engineering systems, and they're usually doing something smart, right? Well, we should model exactly what's being done. That's the point. Figure out how it actually works in the real world, put that into your model. And we can do that in GoldSim, but try to be realistic about how the system is actually controlled. Okay, again, as I said, this was fairly simple stuff. Nothing real ground shaking here, but we wanted to cover this because we see people sending us models that oscillate all the time, and they almost always oscillate because of a bad active feedback control system. I'm going to take all of these models that I've just shown you, and I'll put them up on our website. There's a past webinar section. If you go to our website, there'll actually be this recording, and there'll also be all these model files in a zip file that we'll post up there. And as always, by the way, if you have specific questions about anything I've talked about or anything about GoldSim, we really encourage you to send us questions. We're happy to answer them. Send them to support@goldsim.com, and we can help you out. The last thing I want to say for today has nothing to do with this topic. I just want to give everybody a heads up. We had a little announcement earlier. We'll be rolling this out in the next month. Within the next month or two, we are actually rolling out a new licensing system that's going to, particularly for network licenses, is going to be way more powerful than the system we've had for the last 15 years. We'll be sending out announcements over the next couple months. It'll be on our website. We'll send out a newsletter. Keep your eyes open. It won't be sudden. Your model's not, your GoldSim is not going to stop working. It'll continue to work, and then as need be, you can convert over to the new licensing system, but it'll be pretty cool, and I just want to give everybody a heads up on that's going to be rolling out here in the next couple of months. Okay, well, thank you very much for your time, and as I said, go to within probably early tomorrow, I'll have everything posted up on the website, and as I said, if you have any questions, don't hesitate to contact us. All right, thanks a lot.